Hello everyone, welcome in this video tutorial on modeling of toluene disorder across the symmetry. The crystallographic programs used are OLX2 and Selexel. These programs are available free of charge for the academic users. The necessary files required for the refinement are used with permission from Dr. Peter Muller and from Mr. Sonk Adlan. The more detail about this particular example is available in this very nice book reference, Crystal Structure Refinement, a Crystallographer's Guide to Selexel, edited by Professor Peter Muller. So let's start the tutorial part. For this, I am going to open the OLX2. This is OLX2. From here, we are going to join the refinement. At this point, we are going to join the refinement. Up to now, the refinement is very straightforward and simple. This is the molecule, only half molecule in the asymmetric unit, and there is no solvent in the structure yet. So we are going to refine the solvent part. This is a molecule crystallizes in monoclinic space group P21 by M with only half molecule in the asymmetric unit. The I upon sigma value is very nice, it's around 60, and the crystal quality is very nice. It's diffracting beyond the 2 theta 50 degree. The F observed versus F calculated graph is scattered and it is not looking nice yet. The maximum electron density is around 6.5 electron. Goof value is good. So from here we are going to join the refinement and we are going to model the lattice solvent in the molecule. So from crystallization point of view, we are expecting toluene in the crystal lattice. For this, I am going to press this button first, compact, and I am getting some electron density like this. Here these two electron densities are very low, only half electron. So I am going to delete this. And the remaining electron density is forming some strange type of molecule in the lattice. These two electron densities are around 2 electron and which are significantly lesser than these 5 electron densities. These 5 electron densities are almost 5 or 6 electron. If I am going to delete these, I am getting this type of electron density in the lattice. So if I am going to grow the structure by typing or by pressing Ctrl G, I am getting a such type of electron density which seems to be a toluene molecule in the lattice. Okay, here if I am going to model this toluene by using the fragment dB, since the molecule is across the symmetry, so only half of the molecule is present in the asymmetric unit. So I am going to model the disorder by using the part -1. For this, if I am going to tool fragment dB and if I am going to search toluene, where toluene, here is toluene. So part -1, free variable 1, occupancy is of course only half because molecule is present on the symmetry and going to fit. For this, just select the 3 atoms and match them. This atom will match with this with this. Okay, so that's good. That's nicely fit. If I rotate a little bit like this, now it's looking very nice fit. Press escape, and if I'm going to refine, the R factor will down from 9.5% to 4.88%, and I'm going to find 2 or 3 times more so the shift gets stabilized. Okay, one more time. So now you can see there are some more electron density of around 1.5 or 1.65 electron, 1.65 electron, and around 1.3 electron. So if I press fuse and I'm going to select this type Anis, Rigu, and H add and refine. Now the R factor is further down to 4.43%, and one or two more refinement will settle down the shift, and the R factor is around 4.42%, and F observed versus F calculated graph is now looking very nice. But it's not going to solve my problem because I am still getting some electron density around 1.5 electron around this disorder molecule. So in this way, I can't model this disorder. If again I press the Control G, grow, I am getting a such type of solution. So these two toluene molecules are lying almost one above the other, and I am still getting some qpx electron density here. So this is not the correct method to model the disorder, this type of disorder. In the present case, I have to use some other trick to model this disorder. For this, I am going to select this and press delete, and I am going to define again, fine. I will get back the same structure. The R factor is around 9.4%. Okay. The shift is almost stabilized. Now, let's make the qpx little bit larger for a better visualization. For this, I am going to use this command, assume 200 is the size of qpx. $q all the qpx are now 200 in the size. Now these are looking better, good. So now I am going to press this button compact. Oh, it's not working on ground structure. So let's first type fuse and then press this button. Okay. Now I am getting the same electron density here. So these are very less electron density. So I am going to delete these. Now, if I select these carbon which are quite high in electron density, corresponding to 5 to 6 electron density, and press C to make them carbon. Suppose if I am going to name them systematically by selecting in this order, and I type name 1, so it will give me C1, C2, C3, C4, C5. And sort all the atom in this order, and if I am going to edit the .ins file, I have these atoms here, C1, C2, C3, C4 and C5. The atoms C1, C2 and C5 are only half occupied because these atoms are on the crystallographic mirror, and C3 and C4 are fully occupied. So if I am going to look at the structure, so C5, C2 and C1, these atoms lies on the crystallographic mirror. So these are only half occupied. Okay, I'm going to, yes, these atoms are on the crystallographic mirror. So in this case, the situation is like this. Here, yes. So toluene disorder is across the crystallographic mirror, not across the crystallographic inversion center. It's across the crystallographic mirror. The situation is something like this. So we are getting only this type of structure or this part of the structure, 1, 2, 3, 4, and 5. These 5 atoms we are getting in the asymmetric unit. And out of these 5 atoms, these 3 atoms are on the special position, means these are on the crystallographic mirror, and these are only half occupied, and these are fully occupied. And we have a crystallographic mirror passing these 3 atoms. So this mirror will generate the remaining 2 atoms in this way. And if this is the one orientation, this is the second orientation. In this orientation, the molecule is generated by the crystallographic mirror in the same way. Okay, but in the present case, there are two orientations of toluene which are approximately at 180 degree to each other, and only half is present in the asymmetric unit like this. So one orientation is this, and second orientation is this. And if there is crystallographic mirror here, and we are getting this type of situation in our present case. So the disorder is across the mirror, and the only half molecule is present in the asymmetric unit in two different orientations. So let's come back to the example and let's model the disorder. Okay. Now the trick is just select these atoms and press split same. And now I am rotating the disordered part in such a way yes. Okay. Now it seems to be nice. Now press escape and refine. Refine one more time. The maximum Q is around 1.7 only. So now these two atoms are should be same equal displacement parameter. I select these two atoms and type EADP. I'm going to refine. So okay, these two atoms should have equal displacement parameter for a stable refinement. I'm going to refine. Nice. And these two atoms will EADP. Okay. Now it seems to be very nice. Refine so the shift gets stabilized. Refine one more time. Okay, now Anis, then Rigu, and then refine. Nice. So R factor is around 4.07%. If I going to select the part 1 only, cell part 1. Select the part 1, and now I'm going to add. Okay, so it will add the hydrogen on the first part. So I'm going again, select part 1, and I'm going to open these atoms by pressing this button. So you can see the part 1 is C1 is only half occupied, so I should change these to 20.5. Okay, 20.5 and 20.5, and this is only half occupied. half occupied. This should be C3, so it is 25. It should be 20.5. C4, C5, C5. This also 20.5. Good. Now I'm going to press OK. I'm going to refine. So I'm getting a situation like this. So if I press this 0, 1, so this is part 1 and this is part 2. You still not have hydrogen yet. So if I'm going to press all, now I am going to sell part 2, select the part 2. Now I'm going to add. It will add hydrogen on the second part also. Let's again select this part 2 and press this button. Here C5A is only half occupied, so this should be 20.5. This is 21. This is 21. Okay. This is 20.5. 20.5. This should be 20.5. Nice. C1, C2, C2A, C3A. So I'm going to select part 2 only. This should be half occupied. Yes. And this should be half C2A and this is C5. Okay. So let's refine. Now you can see the R factor is further down to 3.96. Now there is no Q peaks in around this molecule, this toluene molecule. The shift is almost stabilized. Refine one more time, so the shift gets stabilized to almost 0. Good. Now maximum peak is around 1.6 electron, which is around the zirconium atom. So if I am going to press Ctrl G, I am getting a situation like this. This is part 1 and this is part 2. Okay. So it model the disorder across the mirror symmetry. Refine one more time. Let's increase the cycle to 20 for the easy convergence of the refinement. Press this all. Here I'm getting this shift I'm getting here on this atom. Select this atom and type 33. 33. Hope it will settle down the shift this time. Yes. Now the refinement is converges. If I look at the F observer F calculator graph, it looks very nice. Thanks for watching the video.